So I've been reverse engineering hardware for a few years now, and it never occurred to me that I skipped over the almost required learning, installing Doom on unusual hardware. It wasn't until these enterprise time clocks rolled across my bench that I realized that I had the perfect piece of hardware to run Doom on. And I don't mean that in that I can get Doom to run easily on this or that it's the most performant, but I mean that in that it has a card reader. If you've ever played the game Doom, you'll be familiar with the quintessential game mechanic of swiping keycards to get through colored doors. There are usually a few colored access doors that are scattered across the demon-infested facility that Doom Guy is currently romping through, and typically these keycards are required to open the corresponding door of that color. And this got me thinking, can I not only use this hardware to run Doom, but also use the card reader as an input method for the game? Running Doom on this time clock should be a simple matter of transferring the game's code over to the device and getting it to execute. So let's get started by inspecting the device and see how we can access it. First things first, I like to always take a look at the outside of the hardware. So we've got a touchscreen interface, a couple buttons on the front, kind of like an options button and a home button. We've got an LED light up at the top left. Over here on the right hand side is going to be the card reader. Up at the very top we have a biometric fingerprint sensor. And on the left hand side we have a speaker. So I've already taken the case off of this. Let's go ahead and flip it over and see what we've got going on the other side. So over here on the left you can see this is our card reader. We have our biometric fingerprint sensor up here, which is connected to the biometric security module. We've also got our main compute located on this board. This is an OMAP 3503 processor. So that's what's doing all the heavy lifting on this device. Over here on the right hand side we have a set of USB ports, an Ethernet port, and some power and filtering kind of stuff going on. Wait a second, is that an SD card? Well, obviously I'm going to check that out first. And we can go to a informational resource called eBay and figure out what type of power adapter we need for this kind of thing. So let's go ahead and take a look at that. On the screen right now we've got an eBay listing for a Kronos InTouch 9000 time clock switching power supply. So I believe this is probably what we're going to be looking at if we were to connect this up with like the original hardware. So let's go ahead and take a look at this through these images, thankfully provided by Comericos. So we've got a Kronos, that's the right logo. Looks like we're dealing with the right device. If we look on the back of this, we can see the outputs. We've got an 18 volt output up to 2.2 amps for 40 watts. So we know that we need to set our benchtop power supply to 18 volts if we're going to power this thing up. Let's see if we can get an idea of this connector. So that's cool. It looks like it's going to be utilizing the 4-pin Molex connector that's on the board that we saw earlier. And we can tell that only 2 of these 4 pins are populated. And it looks like they are on the opposite side of the clip. So we'll utilize that to narrow down which pins we need to work with when we go to power this thing up. Let's see, what else can we learn from this? Anything else? Kind of a small image, but it looks like we have a white wire and a black wire. I'm imagining one of those is going to be ground and one of those is going to be the actual 18 volt positive. So let's go ahead and go to our device and we'll take a look and see what we can figure out. Alright, so for this task I'm going to bring out the trusty handy dandy multimeter. And we're going to start probing around this 4-pin Molex connector right here and see if we can't figure out how we need to hook this up. Alright. So I'm going to set my multimeter into continuity mode. And we'll find a nice screw on the board that we can use as a potential ground. So I'm just going to grab this one right here. And we'll start probing these points and see if any of them squeal. So that one looks like it's squealing. The bottom left right there, this one is likely ground. And the bottom right is doing nothing, so that is likely our power lead. So what do you do when you want to connect power to a device that you don't have a connector for?
This is where I'd put a trophy. If I had one! Sorry.
Well, you make your own. In this case, I've created 2 power cables. It's essentially a DuPont wire. And I've taken the DuPont connector off one end and I've coated it with some heat shrink tubing. So it's just the raw DuPont female connection on this end and I'm going to slip this into the Molex connector and get that attached to those pins. So if you remember, our ground is on the left-hand side. That's going to be this one right here, the white cable. We'll get that on there. That's got a nice solid connection. And we'll put the gray one over here, and that'll be our positive lead. Remember, we've got our ground on white and positive on gray. And there we go. All right, I've gone ahead and set my benchtop power supply at 18 volts, and I'm going to go ahead and turn this on, and we'll see what it does. I heard it make a little bit of a crackle noise. I can see 1.7 amps being pulled through the power supply. So it is definitely on and doing something. We take a look at the back. We've got a red LED right here, so that's a good sign. And flip this back over. And maybe we'll give it a little bit, and it's probably thinking about something. Oh, you know what? I'm stupid. Don't forget to stick the SD card back in, because oftentimes devices that need SD cards will not boot without them. And immediately we've got a yellow LED right there, and I can see the power supply pulling about 0.2 amps, so it does look like it's doing something.
Three hours later.
But before I do anything to this disk, I should make an image of it and work from that instead. You know, just in case. It's highly recommended that you take an image of this disk, and then you make a backup of that image. And then that way you can work directly from the image when you're doing your sleuthing or your kind of discovery process, and you won't have to worry about negatively affecting the original device or the original SD card. So I'm going to go ahead and show you how to do that really quick. And then the first thing we're going to do in our Linux system is type in lsblock to list our block devices. DevSDC is going to be our 1.9 gigabyte block device. And we can see we've got a couple different partitions. We've got SDC 1, 2, 3, 5, and 6. Immediately I can tell that this is likely going to be some sort of boot partition because it's 54 megabytes in size. It's pretty small, and it's also the very first partition on the block device. We can open up fdisk and check the partition types to determine a little bit more about our file system. First though, let's go ahead and make an image of this before we start messing around with fdisk or anything. What I'm going to use to do that is my trusty old dd command, or as I like to call it, disk destroyer. So we're going to go ahead and type dd, and it's going to need an input file, which is specified by if equals, and we're going to give it the path to our block device, dev sdc, and then we're going to need an output file, of equals, and we'll give it the path to our output file. I'm going to spit that in the local directory, and I'm going to call it lovingly k9000.image. And some extra flags that we can send to disk destroyer is going to be block size 1 megabyte. This will let it copy the data faster. It'll do it in larger chunks. And then we also want to show our progress, so we'll do status equals progress. That dd failed to open dev SDC, permission denied, as it should be. All right, after triple checking this command, I'm going to go ahead and append sudo, run that. And it should start to image our disk. I consider it a good habit not to put sudo at the beginning of your dd command, just in case you type it wrong. It won't actually execute against a block device that you don't have permissions to, or that you need sudo permissions to interact with. One quick disk destroyer command later, and I'm presented with a image file that I will lovingly call k9000.image. So now let's make a copy of that image that we just made, and we'll name that k9000.image.back. You know, just in case, Now that I've got an image file, I can use the Linux utility losetup to create a loopback device, attach the image to it, and scan for partitions. So knowing the path to our K9000 image, what we will do is we will use a couple flags from losetup. You do tac help, and what we're looking for is we're going to use the tac F for find first unused device, and then we're also going to use tac P to do part scan and create a partition loop device. So let's go ahead and run this command, and we'll point it to our file, and it should create a loop device for us. So sudo losetup F and P, and then we'll give it the path to our K9000 image. And if that ran correctly, we can do ls block. And you'll see up here at the top, we've got our loop 0 device, 1.9 gigabytes in size. And then we have our 54.9 megabyte, 1.4 gigabyte, 1K, and then the rest of the partitions. So it looks like it was able to clone that accurately, and now we've got that running as a loopback, or as a loop device from our disk image that we made. So now I'm going to go ahead and unplug this SD card. That way we don't make any accidental changes to it. After having ran that command, I can now mount those partitions and start digging through the information on the disk. Using a tool like fdisk, you can analyze the file system on a block device. And remember, we're going to be working with our loop device. So let's go ahead and type in sudo fdisk dev loop 0. We can type P and press enter to print the partition table. And sure enough, it's Linux. Okie dokie. Now what we're going to want to do is mount this file system to a local folder so that we can start to browse the contents of the file system and see what we're working with. So I'm going to go ahead and type in ls block. And we've got a couple partitions we want to mount. It looks like we've got 5 partitions in total. So let's go ahead and set up a couple basic Linux directories. So if we list those out, we've got 5 directories that we can mount these partitions to. Let's go ahead and start with that first partition. So we will sudo mount dev loop p0 p1, and this is going to go into the boot folder. And looks like that went well, so we'll go ahead and print out the contents of that and see what we've got. All right, cool. As I guessed, it looks like this is the boot partition. We've got an MLO, some uboot binaries, and a uimage file, which is kind of cool. We can dig into that later. All right, let's get that next one. We're going to reuse our command. I'm going to change this to 2, and then this is potentially our root partition, so let's mount that one there. And that one went fine too, so ls underscore or /root. And yep, it looks like we've got a Linux looking file system that we've now got mounted to that root folder. Cool, looks like we've got a couple folders in here. We've got a lost and found, ngddb, ngddb.empty, and a scripts folder. Okay. And we've got one more partition, which is our loop 0 p6. And cool, looks like we've got some more folders. We got an audio, another lost and found, photo folder, and a video folder. All right, cool. Go ahead and clear the terminal. And look at our handiwork again with ls block. And we can see that these are all mounted up under our boot folder, root folder, config, and data. So this should be a good start. We can start digging through this file system and poke around and see what kind of interesting things we can learn about this device. As with most Linux systems, I like to start with the startup folder, such as etc initd, etc systemd, or etc-rc. This helps me understand the device at boot up and what additional scripts and software it calls. So let's go ahead and cd into our root folder, into etc, and we can do an lsla to list all the files. And it looks like we've got a handful of stuff in here. Let's go ahead and try to figure out what kind of boot system this device is using. If you haven't guessed it already, this device is pretty old, about a decade old at this point, which is like 8 billion years in computer years. So it shouldn't surprise you that we don't have many of the modern Linux luxuries such as systemd. But what we do have is sysv init. So what we're going to do is we're going to look for that init tab, and we'll check that out and see what that's got in it, and we can kind of trace it down the chain from there. So let's go ahead and cat init tab. During sysinit, it goes and it runs etc initd, and it runs this rcs script. So if we go check out this folder and this rcs script, that would be the next step in the init process, and we can continue to follow the boot chain from there. And if we check out that script, we get a lot. I won't spend too much time explaining everything that goes on inside this file, but a few notable and interesting things are a couple scripts that are responsible for initializing some EPROMs and setting some passwords. We can see a portion of the script that's responsible for playing some audio during boot up, and a script that sends an image to the frame buffer during boot up. Hold on one second. One section of that RCS script that was called by sysinit is responsible for running every single script inside the etc rcsd folder that starts with a capital S and does not equal s55 sshd. Okay, so I guess I'm getting a little carried away here, and I should probably tell you what I'm looking for. If I'm going to get this thing running Doom, I'd figured that it's going to be a lot easier to have live access to the device instead of constantly removing and reinserting that SD card. Because honestly, I'm getting really sick and tired of removing and reinserting this SD card, and then waiting for the device to boot every single time I want to test changes. And let me tell you, this device is slow. And once I have shell access to the device, I can start to poke around at other things such as active processes and temporary files. At this point, I think it would be straightforward to just enable the apparently existing sshd server, so let's go ahead and try that. We learned that the stock start the sshd server won't actually run because of this check right here. So I copied and renamed the s55 sshd script to a new file called s56.sshd. And then I restarted the host to test the changes. And nothing. When reviewing the startup scripts, I noticed that a couple of them were actually outputting their logs to a file called barlogprestartup.log. So I checked that to confirm whether or not our s56.sshd script was actually running at boot up. Sure enough, it looks like it is firing off, but maybe there's some sort of check elsewhere that we're not actually passing. So I go back and I review that sshd script, and there it is. Start sshd only when it is enabled in etc rasconfig.ini. We're going to have to edit that file, change the flag from false to true, and then try it again. And then once the device is up, I'll run nmap one more time. And yep, we have an SSH endpoint. So now I have an SSH endpoint, and when I try logging in, I'm presented with a typical SSH login. And the typical SSH login problem. What username and what password do I use? I can check the password generation script and see if there's anything useful for me there, but I really just need to find a remote management endpoint or set up a shell that I can use to connect to this device. At this point, I tried changing gears and I tried setting up a couple backdoors instead of relying on troubleshooting those SSH scripts. After one quick trip over to the Linux shell store, I'm left with a couple of good options for popping a shell. I'll compare these options from GTFO bins with executables that exist on the system, and then try out a couple methods to see if I can get those to work. Armed with that knowledge, I went back to the SD card and started staging some shells in some known startup scripts. I think my best bet here is to stick some of these backdoors into some of the startup scripts that I know are executing properly. Now I start my netcat listener and I fire up the device, and this time without the suck. Only to be met with the same results as last time. Nothing. Okay, so let's do something smart for once and take the errors that our scripts are generating and redirect those to a file that I can review later. So I edit the scripts and add a simple redirect to a file called ripandtear.log. In retrospect, I probably should have named it ripandtearmyhairout.log. When I fired up the device, I figured, hey, even if my shell scripts don't work, at least they'll log their errors this time. And sure enough, everything starts working. I catch the reverse shell with my netcat listener. Let's come in here to reports. We're going to go down to network, click on that, and we should see our shell get popped. And then I scan with nmap, and I can not only see my bind shell on port 444, I can also see the SSH server listening on port 22. So now that I've got a live shell on this device, I'm faced with a problem. The live shell kind of sucks. If you've ever used a janky shell on a device before, then you'll know how annoying it can be. So when I send Control-C to close the existing process on the remote host, it actually closes the entire shell that I had open. If you were a real threat actor, it would be extremely upsetting to see a reverse shell vanish just like that. The network info script that we put our reverse shell into gets run on a regular basis, so all we have to do is start our netcat up again and wait a couple minutes and we get our shell back. This is what we call persistence. So at this point, I turn my focus back to the SSH service in order to get that working. With the SSH service running, I tried connecting, and I was obviously met with a couple errors as I tried very basic passwords and username combinations. No matter, I'll just set a new password for the root user through my reverse shell. So it looks like that worked, but as it turns out, this SSH server is configured to only allow one user to log in, and that's the RA user. So we go and we edit our sshd configuration file, add our root user as a valid SSH user, and Bob's your uncle. One small config change later and a restart of the sshd service, and we're able to connect with our new password. Now that we have a complete live shell to this device, I can get started on the Doom parts of this project. And for that, we've got to learn about cross-compiling. So first we'll need to figure out our target triple. What is a target triple, you ask? A fellow practitioner of the dark arts, Miguel, who knows a lot more about compilers than I do, speaks in great lengths about target triples on their WebZone post. Basically, a target triple is a wibbly-wobbly, stringy kind of thing that describes the target environment that we want to compile our code for. This target triple is usually provided to a build system so that it can properly cross-compile a usable binary for our target system. Originally, the target triple was just 3 pieces of information, hence the name, but nowadays it looks a little bit more like this. There isn't really a standard here, but they generally follow this premise. Now if I just fill this in madlibs style, we should be left with our target triple. Architecture refers to the language that the CPU speaks, and for our purpose we're going to specify ARM, but it could be others like x86, 64, or RISC-V, or something completely different. Subarchitecture is sort of like a version number. The target that I'm working with uses ARM v7, but I don't think we actually need to specify this for our compilation case. The vendor is also unnecessary for us to specify because our toolchain doesn't have any vendor-specific implementations. So we can just write this as unknown. System refers to the operating system that the target is going to be running. It can be anything from Linux, Windows, Apple Darwin, Android, or something else. And finally we have the environment. Typically this refers to the compiler environment, and in our case I'm going to specify GNU EABI HF, which is short for the GNU C compiler for ARM EABI with the HF hardflow option.
Hell no, man. What the?
Now that we know our target triple, we can head over to ARM's website and download the toolchain. Thankfully, ARM provides some ready-made toolchains for compiling ARM targets, so this removes a ton of complexity from the process. Once we've downloaded the toolchain, we can extract that to a known location, and this is going to be our toolchain build root. At this point, it kind of helps to know what a few of these folders inside this toolchain are actually used for. Firstly, we have the bin folder, which contains all of the toolchain binaries that are going to be used to cross-compile code for the target. Secondly-ish, we have another folder named after the toolchain itself, ARM None Linux GNU EABI HF. There is also a lib folder, which is where we can place all of our external libraries that will be used during compiling. Remember this folder because it will become important for later. Now we need to add our toolchain to our shell path variable, and to do that I like to change directory into the toolchain bin folder and then run the following command. Alternatively, you can manually type the path to your toolchain bin folder and add that to the end of the path variable, but I find this is a lot quicker and more accurate. At this point, we've got our toolchain in place, and it's time to move on to the compilation step. And for that, we'll need some code to compile. Searching for a suitable Doom port is surprisingly straightforward, but the potential for rabbit holes is immense. Simply scroll through the list of Doom source ports on the Doom wiki until you find one that is suitably basic enough for your hardware. And after some searching, I finally came across a suitable Doom port called fbdoom. This port seems suitable due to the low number of dependencies required to compile it, and also the fact that it natively supports a Linux frame buffer. So I'll go ahead and clone this repo and take a look at the makefile to see what we actually need to change to cross-compile this code. At the top of the makefile is a cross-compile variable that we can use to specify our toolchain. This should be enough for now. So from the fbdoom folder that contains the makefile, I'll go ahead and run the make command with the cross-compile flag just to get the errors flowing. Immediately, I'm greeted with a lovely compilation error that complains about using keywords as enumeration constants. A simple modification of the game code and a rerun of the compilation, and I can see that it makes it a lot further now. Until it aborts with a new error, this time whining about not being able to find libSDL. Which makes sense, because apparently when you cross-compile code, you also need to cross-compile the external libraries that code depends on. So at this point, you kind of just chase error message after error message until you either give up or you're left with the working binary. And I'm not giving up yet, so let's go find libSDL. In a similar process to fbdoom, I'll locate the libSDL 1.2 source code and pull that down into my build folder. For some open source projects, you'll find a configuration script, and typically this configuration script is responsible for setting up the build's properties prior to compilation. Eventually, I checked the help page from the configure script, and I learned that I can specify cross-compilation by using the host flag with our target triple that we learned earlier. So after running the configure script with the appropriate host flag, I can now run the make command and let the compiler chooch. Eventually, I am faced with another error message sobbing about Pulse audio libraries not working. So I consulted the internet and also went back to that configure help page and eventually learned that I can just toggle the Pulse audio libraries off with a specific flag to the configure script. And you know, between you and me, I'm not looking to debug Pulse audio libraries, so I'm just going to turn that off for now. Once I had that reconfigured, I cleared out the old build files and reran the make command. Eventually the build completes and I'm left with a fresh.libs folder that contains our library cross-compiled object and assemblies. Remember that libs folder from earlier? This is actually where I need to copy my froggyfresh library files to. So I grabbed the libsdl.a file and stick that into my build root lib folder, and I head back to the fbdoom folder to run a recompile. Now that I've got the libsdl library files added to my build root, I can try compiling fbdoom again. So I run the make command again, and there we go, we've got a fresh new binary. I can then run the Linux file command against our new binary, and sure enough, it looks like it's an ARM compiled ELF file. This looks like it should work, so I'll secure copy protocol this file over to our target time clock, and then I'll SSH in and try to run the file. So it looks like it didn't run properly, and after doing a little bit of research, I determined that the reason why is because the dynamic linker we compiled it with doesn't exist on the target system. No matter, there are two ways to solve this problem. The first and recommended way is to compile the binary with the same dynamic linker that is on the target system, or copy the dynamic linker to the target system. The lazy way is to statically compile the binary so that the required libraries are effectively embedded within it, and no dynamic linker is necessary. Statically compiling your binary will result in an increased file size, and it can cause issues when shared libraries are being used, but I'm willing to take that risk. So I can take the easy route by going into the fbdoom makefile once again and adding the static flag to the LD options variable. With that set, I can rerun the build and check the resulting binary with the file command in order to determine its statically linked ways. Cool beans. So I'll repeat the copy and run process that I did earlier, and it looks like it works. Well, it works in the way that it now fails to find an iwad and properly gives me a real Doom error. After copying over the Doom demo.wad and passing that to the binary with the iwad flag, I now can run Doom on my time clock. That's neat. Okay, so the sound doesn't work and the resolution's all borked up. What are you going to do about it? Subscribe? Anyway, at this point I'm left with one last task, and that's to get the card reader working in-game. And to do this, you'll just have to wait for part 2, where I share more details about this ancient time clock while I try to integrate a card reader into a game from the 90s. If you enjoyed this, then feel free to leave a like on the video, and if you want to see more stuff like this, feel free to check out my live streams where you can watch me stumble through projects like this one, but live. A special thanks goes out to my Patreon and YouTube members, where their support goes directly to the coffee and the hardware necessary to make these videos happen. Bye!